All right, so you're all going to get a note if you're on that this meeting is being recorded, and I will put that up here. And we'll give it 1 or 2 more minutes just to see who decides to show up. Okay, I'll wait just a couple of minutes, but we can just chat while we're waiting.
Max, has my dog moved yet?
Yeah, he went to a different bed, and then now he's back in the same bed.
Okay. Is he depressed? Do you think he's depressed?
No, usually his depression is like he sits and whines the whole time, but he's pretty content. I gave him a treat, and he wasn't super excited, so maybe, I don't know.
So one of y'all needs to add DB to the last group. I'm only a content manager, not a.
Yes, we can. Yes, we can. Okay. So for those of you that are new, which is about half of you, I think, I decided about a month ago that I was going to start teaching ThermoCalc to my graduate students. And last week we had our first session. And I just decided that seeing how I'm doing this for my students, it's an informal thing and it's not going to be any more work for me to invite additional people. And so I opened it up to the rest of the material science department. So all of the faculty got their emails, and and I think most of them forwarded to you guys. And if you were interested, shot me an email, and now we're going to have a group. I don't know how many people is going to be here. Like I've said numerous times in the emails that I sent out, this is quite informal. Last week, I didn't even come in with much of a idea of exactly what I was going to do. This week, I actually talked to Serena for 2 minutes, so now we know what we're going to do. But the whole point of this is to give you guys some very basics to get you started on ThermoCalc, and then you guys can play around with it. To start with, if you don't have access to the full version, you can use the demo version. I'm not sure if there's a time limit on the demo version or if it's just a features limit. Is it a feature limit?
It's feature limit, yeah.
Okay, so you can use the demo databases, and it only goes up to ternary alloys. So you can do almost everything you want to learn using those demo databases. And once you get to the point that you want to start working on it for your research, you can come talk to me, or you can talk to Suresh Babu as well, and we will get you access to the full version of ThermoCalc so you can do your thing. I am recording these so that anybody who doesn't come to these sessions or wants to look at them again can go take a look at them. They're at our group website, our group webpage, phase-trans.utk.edu under course information. So if you're interested, you can always go back and take a look. The class from last week is up there, so if you didn't take a look at it, the first thing we did is we just gave an intro to what ThermoCalc is when you open it up, which I'll do today, and then we learned how to calculate a binary phase diagram several different ways. So this week, we're going to talk about plotting thermodynamic functions. So plot the Gibbs free energy, the entropy, the enthalpy as a function of temperature for a single phase system, and then to plot a free energy curve for those of you that are in the thermodynamics or the phase transformations course. We've seen a lot of free energy curves. So we'll look at how to plot free energy curves in a binary system as a function of composition. Then we have time, we'll move on to a ternary, plotting ternary phase diagrams, and then a Scheil solidification module will be the last thing, assuming we have time. I have a hard stop at 4:30. I was not planning on our last meeting to last 2 full hours, but I like to talk, and other people in my group like to talk, so that it took 2 hours, and we had fun doing it. So I hope everybody has fun and learns a little bit while we're going. If you have any questions, please feel free to ask. If you've got multiple monitors and you have ThermoCalc installed, I will use one of the demo databases so that you can actually follow along and try to do it. Try to do the same thing while we are learning. Any questions before I start? Cricket, 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 cricket. Cool. So I shall share my screen. All right, I'm going to open up ThermoCalc. See what we see. So the first time you open up ThermoCalc, it will open to what we call the graphical mode. This is easy mode. We went through calculating a phase diagram. Last time using easy mode, but to be completely honest, anything that we learn in console mode is pretty much self-explanatory in graphical mode. So everything that I do from now on until we start talking about the precipitation module, I'm going to do in console mode, and you'll find very similar commands under the graphical mode. There are 3 basic modules to using ThermoCalc. There's ThermoCalc itself, which is an equilibrium thermodynamics system. There's a diffusion simulation module called DICTRA, D-I-C-T-R-A, that you can solve one-dimensional diffusion problems in. And then the third module is relatively new, and it's only available in the graphical mode, and that's called TC Prisma, which is a precipitation simulator. There are also several other things that have been added since the graphical mode has been added, like this property model, STI library, TTT diagram, process metallurgy. A lot of it is metals oriented. I think most of us are metals people. I won't say everybody because I don't know for sure. We can actually open up the property calculations, because this is where, if you have a steel or something like that, you can actually calculate the martensite start temperature as a function of composition. Let me just see what this looks like. Let's go to property model calculator. So yeah, you can calculate coarsening, crack susceptibility, different transformation temperatures, martensite start temperatures, martensite fractions as a function of temperature. So there's a lot of things in here. I will be honest, I've not used these as much because they're considerably newer. And so, and I haven't used them, but they are there. They are designed for specific materials. Like you saw, one was for a steel. And so there's a lot of different information in there for specific types of materials, steels in particular, some nickel-based alloys and so forth. What we're going to do most of our calculations in is the console mode. And so the first thing we want to do this week is we're going to plot functions as a, we're going to plot thermodynamic functions for different systems. When you open up ThermoCalc in console mode, you'll be under the sys command prompt. What's that? Oh, yes, yes. The first thing you want to do, and like I told my students last week, is I'm horrible at doing it, is you want to set log file. Because what that will do is it will create a log of all of the commands that you put in, and it will be saved as a .tcm file, which stands for ThermoCalc macro file, which you can then open up again the next time you open ThermoCalc, and it will run through all of your commands. So it makes things a lot easier. You would not imagine how many times I've typed the same thing in multiple times because I don't use the log set log file as much as I should in the macros. I'm getting better at it, but I wouldn't have done it if Serena hadn't said something. What's it? Yes. So I went set dash log, and anything you type in these command prompts, you can put all sorts of abbreviations in as long as it's unique to the set of commands. So if I go SL, there's only one of these commands that you see up here that's SL. So SL, ThermoCalc will know, set log file, type in the log file name and save it. It'll ask for a heading. I don't think I've ever heard anybody use heading, and now it's recording everything that we do. If you have two things that have similar names, like set poly environment and set poly version, if you just go set poly, oh, it does. Oh, yes, set P, it's ambiguous. So it doesn't know which one of these two it is. So whatever you do, you can use any type of abbreviation you want. You can use dashes, you can use underscores, but whatever you put in at the command prompt has to be unique. So the first thing that we want to do is go to database. So anytime you need help and you get lost, question mark enter will give you all of the different commands. The first thing we want to do is go to module and ask module name, question mark. These are all the different modules that are in here. First thing we want is the database retrieval. So D. Then it comes up. The default database is the ThermoCalc TCFE9 Steels database. If you're using the full version, if you're using the trial version, I think it's the FE demo. So we'll switch the database. When you do that, it'll list all the databases that are available to you. And let's use FE demo. So type in FE demo. I don't even know what elements are in here. Okay, so it's got iron. So the FE demo database has iron, chromium, carbon, nickel, and manganese. So let's just start. What can we do? We can define elements. What's that?
The LD was list data.
Yes, LD was list data. So yeah, so LD is list data. Let me turn the lights down here so we can hear. Better?
Yeah, that's much better.
All right, so If I stop talking, it's because I fell asleep.
No.
No, it's just L/D enter. Oh, and then it asks you, yeah, it's an E.
For elements.
Elements, species, phases, or constituents. Elements is obviously elements. Species and constituents, I don't know the difference between species and constituents. There are, if you're considering say an ionic solution or the gas phase, you can have multiple different species of, say, iron as ions, because you can have different oxidation states. So let's look at species. Here, there's only, when you're doing what? It's LD for list data. So on the different species that are in here are atomic, carbon, chromium, iron, manganese, nickel, and then different species of carbon. Carbon molecule, a carbon-3 molecule, and a buckyball, a C60. Let's see what constituents are, because I don't know for sure. Oh yeah. Should I just type in constituents or phases? C, constituents. Oh no, you know what constituents is? It is giving you what species can go on in each phase. So, yes, so sub L is sublattice. So this is actually telling you for the BCC phase, there is 2 sublattices, and the number of sites of each sublattice are 1 and 3. And that is 1 substitutional site plus 3 vacant or interstitial sites, because carbon is interstitial, that we almost always include the interstitial sites. And so we have 1 substitutional site, 3 interstitial sites. For liquid, there's only 1 sublattice. There is no interstitial site. FCC, again, we've got 2 sublattices. This time, there's 1 substitutional site. It's not taking the entire unit cell. It's only taking the number, basically the ratio of sites. And sometimes, depending on the database and what you're using, these will be fractional sites. So if you have say a BCC B2 system, you might have sublattice 1 be 0.5 sites, sublattice 2 be 0.5 sites, and then the third site, which is the vacancies, be 3, right up here. Because when you calculate the molar free energy of your system, it will be based on the number of sites, plus anything that any goofiness that you have because of vacancies, because that gets a little trickier too. But that's more detail than I really wanted to go into. But now you've seen that. So if we list elements. Oh, I didn't list the system. So we're just going to start with iron. So if we look under our command list, I'm going to define elements, FE. It defines iron. The next command we want is get data, G. And it will retrieve the data from the database. So now we have all of the data for all of the phases of iron loaded into ThermoCalc.
Can you do that for multiple elements?
Yes, absolutely.
Okay.
We will do that in a few minutes. I want to start with just a binary,
Okay, perfect.
start with just a unary system. If you look at the last week's video, we actually started with a binary iron-carbon system, and we calculated the iron-carbon phase diagram and the iron cementite phase diagram, which is the metastable phase diagram. So yeah, if you wanted to do it, you'd go define elements, FEC, CR, whatnot.
Oh, okay.
Right. And then so you just define all the elements in your system, and then you go get, and it collects all of the data that the database has for those elements in the phases that in which they're defined.
Thank you.
So I'm going to reject the system to start. So I've basically just cleared out my database. So I'm going to define elements FE. I list data phases. I just want to see what phases are in there. So then I'm going to get. And now, once we get the data, we want to go to our next module, go M. And the module that we use to do all of our phase diagram calculations and all our thermodynamic calculations is called Poly 3. Or you could say Poly, or I usually use P3. And so in this, we've got a lot of different commands. The first thing we typically start with, if we want to plot something, is set our axes variables. And so what we want to do to start with is just plot the free energy of the different phases of iron as a function of temperature. So we want to set axis variable 1 for the first axis. So let's set axis variable. First thing it asks is axis number 1. Condition, T. Min value, I would say 300. Temperatures, when you're doing the calculation, are always in Kelvin. When we go plot something, we can change the temperature scale, but when you're in Poly 3, it's always in Kelvin. So if you say what condition or what variable do we want to have, you type in T, that's temperature, and it's always in Kelvin. So minimum value 300, maximum value will go up to 2000 Kelvin. Increments for temperature scale, I usually do a temperature scale of 10. So one of the useful commands is list conditions. So if you list your conditions, it will list the conditions that we've set. We've set temperature. When you define an axis, you can see it automatically defines or sets an initial temperature condition. We still have 2 degrees of freedom left. What's that? Way down here at the bottom. Yes. You have the 2019 version. So in the versions before TC 2021, which I'm using, when you define an axis, it automatically defines the 2 other conditions that we have to define. The number of, yeah. What's that?
I can't go to the Poly.
Go Poly. What command prompt are you under? You can't go? Give me a second.
You might not need to add the go. That messed me up earlier.
Well, if you go poly straight from the TD epi demo, it should, like, unless you do the go M, then you need to type in poly.
Did you put the license? Same. Oh, you know what, you know what, you know what, you know what? Type in your username, which is your, yeah, your NID plus your email address. So use @vol728ID.
Okay, what was that? What was that comment that somebody said? Sorry about that.
Oh, I was just saying that earlier, if you type go in front of it, it does not accept it. So, yeah.
Oh, it what? Go.
So when we were under module name, if I tried
Yeah.
go poly, it would not allow that. You just type poly.
Oh, yeah. So if you go M, then you type poly.
Yeah.
Right.
Yeah.
Okay, so once you get that's weird. So once you get familiar, did you get it? Log out and log back in. So once you get familiar with ThermoCalc, you'll know some of the commands. And so, for instance, if you open up ThermoCalc and you know you need to go to the database, you don't have to go M and then select database retrieval. You can just go TA, and it'll take you directly there. You could also go P3. So that's why I might have got confused. So yeah, so if you're just at the sys command, at the system command prompt, you can go to any module you want. Okay, so this conditions. We've set our access variables, so we have a temperature condition. The other two conditions that the older versions of ThermoCalc automatically define are the number of moles, N, is equal to 1. So that means every quantity that we look at will be on a molar basis, and pressure, P. And it always sets the number of moles equal to 1. Whoop, go away. The number of moles equal to 1 and pressure equal to 1 times 10 to the 5. So then, if we list conditions again, degrees of freedom is equal to 0. That means we can calculate an equilibrium, so which is CE, compute equilibrium. The next thing we can do is list equilibrium. And it'll ask you, do you want to output it to the screen or the file? If you want to output a specific equilibrium to a file, you can type in file and it'll open up a box, and you could save it. Most of what we do is to the screen. These options I defined last week, so you can go back and take a look. The first one is the fraction order, meaning how is it going to list the phases? Either the value, meaning the amount of each phase, or A, alphabetically. B, the fraction type. So what fraction are we talking about? A mass fraction of each phase or a mole fraction of each phase? The next one is the composition.
So anything within the slash is default.
Anything within the slash, the first time you open it up, it's default. But if we were to do this calculation, and when it says options, we go say V, W, NS. The next time we list an equilibrium, it will remember that we had NS.
You don't necessarily have to run this math.
What's that?
Would I have to have this macro open to do that, or is it just automatically?
It would automatically assume that. So anything that's in your macro file is exactly like what you're typing in. So you'll see. I'm going to use this once I get done, and you'll see it. And I'll show you in just a second. So this third, let me get through these other two. This third letter is composition, which you can choose C for the composition only, which will give you the mole fraction or the mass fraction of each element in each phase, or it will give you the composition and the constitution. And what the constitution is if you have multiple sublattices, it will tell you the site fraction. So that becomes very nice if you're looking at, ordering reactions, and you want to know, it's nickel aluminum, it may be nickel aluminum L12, so it's Ni3Al, but it's not necessarily perfectly stoichiometric. And so the aluminum sublattice may have 20% nickel on it, and the nickel sublattice may have 15% aluminum on it. So when you want to know those types of things, you type in N for constitution. And the final one is which phases do you want to include? Typically, I always use S for the stable phases. So that's only going to show us the stable phases in the equilibrium condition that we just calculated. The other is to include all of the non-suspended phases, and you may want to do this if you're interested in, say we've got a single phase BCC alloy, BCC material, but we know that iron is getting fairly close to being stable. If you list all of the non-suspended phases, it will actually give you that FCC phase that is unstable, and it will also give you a driving force for its formation, which will be negative or positive. I can't remember what it is in here, but it will tell you that it's not, there's, driving force is negative, so it doesn't want to form, but it will tell you how far away from the equilibrium line that it is, how far above it is. So it will give you how really close it is to being stable. So we will get to that when I get to, maybe we'll get to it today, maybe we'll get to it some other time or next week. But yeah, we will get to that. That's something really, really cool. I use it a lot because I think I've mentioned it to some of my students before. But if you want to look at the precipitation of a second phase from a single phase, what you do is you don't suspend the phase that you're interested in, but you make it what we call dormant, so that it will run all of the calculations, but it won't consider it as an equilibrium phase. So if you have FCC plus BCC and you start out with FCC iron, but you're at a condition, at an equilibrium condition where the BCC phase should be stable, if you make the BCC phase dormant, it won't calculate the equilibrium. It will calculate the equilibrium without the BCC, which if it's pure iron would just be FCC. But it will also give you the driving force for the precipitation of that BCC phase. And if you're in a multi-component system, a binary alloy, it will give you the precipitate composition, not necessarily the equilibrium composition. If you take my phase transformations class, you know that's different, right? The equilibrium composition and the composition at which it precipitates is different, and it will actually give you the driving force for precipitation of a phase of the ideal precipitate composition to form. Exactly. Capillarity effects. You also want to maximize that driving force, and that's parallel tangent construction. As we go off on a tangent, talking about tangents. Wow. I warned you, it's informal, everybody. So I have listed an equilibrium. And so what does it do? I did VWNS. It tells us the status for all of these phases. I think this is something new in 2021. I don't think,
I don't have.
yeah, okay. It does not,
I don't
does
see it
not
on the
always-
educational version of 2021 as well.
you can?
I cannot.
Oh, okay. So it must be, what am I doing? What is? Doesn't tell me. Why isn't it telling me what this? What is yours telling you? This equilibrium, LE. Screen. Yep. Oh, yours is good. Yours does the right thing. Why? But why am I listing this equilibrium?
You have 0 moles of iron.
What's that?
It's showing that you have 0 moles.
Did I say? But I put one.
Huh.
That is really weird. Give me 2 seconds. I'm exiting this version of ThermoCalc and I'm going to the old version of ThermoCalc. No, I have both 2021 and 2019 on my computer. Yes, maybe. Oh no. Well, they have possibly the new version, but you'll at least be able to see what it's supposed to show. And I know it does not behave that crazily in binary mode, so it's only an issue with unary systems. Okay, so set log. What's that?
This is the speed version.
Yep. FE demo. Ah, that's much better. Yep. So list equilibrium. Let's list equilibrium. VWNS. I told you I've done this a gazillion times because I don't use log files. Because every time I open ThermoCalc up and I want to do the same calculations, because I don't use log files. I just go blip, blip, blip. So this is what an equilibrium, list equilibrium is supposed to show you. Is anybody online getting the same, is everybody online that's following along getting the same thing I am?
It is exactly the same.
As what I got before?
Yep.
Okay. I will make a note of that, and it's something that I will actually send to the folks at ThermoCalc and have them look into it. So I apologize, you're not going to be able to follow along like I was hoping. Maybe you can. Maybe it's just the list equilibrium command that's all goofy.
Or no, I'm saying I am on the 2021 version,
Yes.
and mine is showing what you are showing here.
Okay, perfect. Okay, perfect. So whatever it is, it's on me. I have no idea why mine was showing something goofy.
Yeah, we made you backtrack commands, so that's my guess.
What's that? Yeah, that's
We had
true.
you. Yeah.
That's true. So we'll just continue. So now, when you list equilibrium, it starts out, what are the conditions? These are the conditions that we set. It gives you the total number of moles of components, the total mass of the system. It gives you the total Gibbs free energy of the system, the enthalpy of the system, and the volume of the system. There are molar volumes in the databases. For the very well-known systems, iron carbon, iron nickel, nickel aluminum, those volumes are pretty good. When you get into large multi-component systems, I don't know how much optimization they've done, because in order to optimize these databases, you need experimental data, right? So if you were to go out in the middle of, quinary HEA space, it may be a little more difficult it may not be quite as accurate. If there is no data, it just assumes a simple Vegard's law, which is a rule of mixtures for the lattice parameter. But it does give you molar volume, which is nice because it gives you a volume. And because we have 1 mole of components, this is the molar volume. But we can say show value, and I'll say VM Okay, so that's the molar volume. I'm just showing the molar volume. We're getting ahead of ourselves here. That is in cubic meters per mole. So back up to list equilibrium. Why this volume is different than the volume we just looked at, I don't know. Oh yeah, because that's because there we go. So this gives us the molar volume. It's calculated molar volume for all of our phases. So here's the molar volume of our equilibrium phase BCC. Here's the molar volume of our FCC phase. What's really nice is if you need a volume strain energy for a phase transformation, a solid state phase transformation, there you go. There's your change in volume. If you're looking at a superalloy, say a nickel-based superalloy where you've got your FCC matrix phase and your precipitate phase L12, your gamma-gamma prime microstructure, they're cubic. If you have the molar volumes, you can calculate the lattice parameters, you can calculate the lattice misfit, which is a parameter that you need if you want to look at mechanical behavior. So there's a lot of really nice data in here, particularly as they've added the molar volume. Is it B? I can't remember. There's also elastic properties in here as well. The compressibility, I can't remember if it's not B, that's something else. B, that's the number of gram, the weight, I guess. But there's also elastic properties in here as well. So there is a relationship between composition and, say, or bulk modulus. I think that's the only elastic property in here. And I can't remember what it is. It might be B, it might be K, it might be C. I haven't used it in a long time. But I'd further digress. So if we go up here, if we look at the components, it actually tells us how many moles, the weight fraction. So that's the mole fraction. Because we have 1 mole, that's the weight fraction. It's 1 and 1. This is the activity. It gives us the chemical potential of iron at equilibrium, which is nice. And it gives us the reference state. We're not going to talk about the reference state much because I almost never change it, because if you don't pay any attention to it, everything works out. If you remember or you've taken the thermodynamics class, you need to basically anchor where your free energy is to a specific value of a specific phase at a specific temperature. It is arbitrary, but the standard state is the I can't remember. All of the free energies are related to the free energy of the phase or of the element in its equilibrium phase at standard temperature and pressure, which is 298 Kelvin and 1 atmosphere in the non-magnetic state. So if you don't pay any attention to it, if you never change it, you'll be good, because everything is set relative to that. And when we go in and calculate a binary phase diagram where we've got something like BCC aluminum, somebody's went through and actually calculated the difference in free energy of FCC aluminum compared to the hypothetical BCC aluminum. And so they relate the free energy of BCC aluminum to the free energy of FCC aluminum so that everything is consistent. Okay. So, and then after it lists the components and the different things about the components, it lists the phases that are present. In this case, because we have a unary system, we have just BCC, gives us the mole fraction, it gives us the volume fraction, it gives us the mass fraction of each element. When we get to a binary system, you'll see that that's not 1. It also gives us the constitution. So on sublattice 1, which we have a total of 1 lattice site, it's 100% iron. Sublattice 2, we have 100% Va, which stands for vacancies. If we had carbon in it, because carbon is an interstitial, the carbon would actually go into that sublattice 2. Okay? So we've calculated our initial equilibrium, and that gives us a starting point to calculate the free energy as a function of temperature. So the next thing that we want to do is we want to run a step calculation here. So step with options is the long form, but it's just ST option. You can do it normal. What normal does is it gives you the free energy of the entire system as a function of temperature. There's a whole lot of other things. What we want to do is we want to calculate each phase separately. So if we type sep, it'll run the calculation, bingo, bango, bongo. It brings us back. Now we want to go plot that. And the plotting module in ThermoCalc is called post. It sets automatic diagram axes. I don't know what they are. What does it give us? Nothing much. So when we go into post, if you do a binary phase diagram, it does a pretty good job of setting reasonable diagram axes. But for this case, we want to start by setting our diagram axes. So set diagram axis X. Let's do it X TC. That's temperature in degrees Celsius. If you want to do TF, that's T-F. If you want to do Kelvin, just T. Set diagram axis Y, let's do GM for molar Gibbs free energy of BCC. Plot it. Boom. This is the free energy of BCC iron as a function of temperature. But was somebody okay?
First plot. Yeah,
What's that?
I was cheering.
All right, our first plot. We got there. It only took us 51 minutes. 50 minutes because we started a minute late. Okay, this doesn't really give us a lot. It gives us one line. One thing that we might want to be interested in is the relationship between two different free energies of two different phases. So set diagram axis Y to GM. Star is the wild card, and that means everything. It'll ask for column number. I'll say enter star. If we plot it, it now plots the free energy of all of the phases that it calculated. And that's all of the phases that by default are in the pure iron system that ThermoCalc did. Can't really see it. Go ahead.
How do you add a legend?
That's the very next thing. Set,
Oh, okay.
where am I? Oh, set labels. Set label curve option. Set label ABC. I don't know. We had a big, let's do this again. Set labels, I usually start out with F. So set labels F. What is F? As D with changing colors. What is D? As C, but colors with same quantities have the same number. What is C? List axis quantities. E is the same way. As B with changing colors. What's B? As A, but curves with the same fixed phase and the same number. And A is list stable phases along line. Let's try, I always use only either F or E. And because these things are labeled so crazily, I really don't know what they are. So I always start with F and see what happens. Hey, look at that. That actually does pretty good. Probably because, which you probably don't have Lave's phase.
No, I do. I don't have the B, no, I don't have the CBC.
Yeah, the CBCC and the A12 and the A13. It's a difference in the versions of probably the databases, either the databases or ThermoCalc or both. Because what we did is we just defined our element iron, we collected the data, and for each system, there's some random algorithm that says these phases are relevant for the given elements. It's not random, obviously, but I don't understand why cubic BCC A12 is relevant for pure iron, but apparently the Thermo-Calc FE demo database thinks it is, so it gave it to us. We can actually, when we collect the data from the database, remove those phases, and when we go back and calculate the binary free energies, I'll actually do that. Okay. So there we go. We plot all of them as a function of temperature. Now, one thing we can do is if we go back, BA for back, it goes back to the last thing. So now we're in poly again. One thing we can do is change status. Phases. So we're not interested in CBCC or cube A13 or Lave C14. So if we list C, BC, BCC, A12, BCC or cube A13 and Laves, I think I can just say Laves, and say, oh man, a lot bigger than I'm hoping it. For phases, the status for a phase can be entered, suspended, or dormant, or fixed. Suspended means we're not going to consider it. Dormant means what I said before, we're going to consider it, but we're not going to make it part of our equilibrium calculation. And fixed means you can actually fix it to be a specific number of moles. And that's useful if you want to calculate something like the liquidus phase or the liquidus temperature for a specific alloy. So if you start your equilibrium calculation up in the liquid where you know the material is liquid, you run that calculation. Now, if you don't set a specific temperature, but instead you set a fixed phase for whatever your first phase to form is, with iron it would be BCC. If you set the BCC phase at a fixed number of moles equal to 0, and then recalculate that is going to calculate the temperature at which the liquid phase just becomes stable relative to the BCC phase. So there's still 100% liquid, but if you drop any lower in temperature, we're going to get a finite amount of BCC. We can actually do that in just a second, but for now, oh shoot, change status, phases, sus, do our calculation again, we step it, oh shoot, post, uh-oh, sorry, I've got it, I forgot. Let's reinitiate the module. That basically resets everything because sometimes it goes a little funky because you can see that it still plotted these guys because we plotted it last time. Okay, so what I did is RM for reinitiate module. Now we'll change status, phases. We don't care about these 3 phases, so we'll suspend these phases. Now we will set axis variable 1, T, 300, 2000, 10. Now if I computed the equilibrium, now if we step separate, it only considers those 4 phases that we're interested in. Now if we go to post, we can set diagram axis XTC, set diagram axis YGM star. Sure.
Why did you say separate? After you said that.
Because and when I post these, set label F. Boom, we're done. Because what the separate or back. Now you can stare at the pretty graph. Step set is separate phases, which means that when it calculates each equilibrium at each interval in your, or each grid in your 2-dimensional, or each step in your 1-dimensional calculation, instead of calculating the equilibrium, it will calculate the properties of each phase individually. Okay, does that make sense to everybody online? Sure. Okay, so if we, oh shoot. Let's see what happens. Step normal. If you look, it actually now calculates the equilibrium free energy as a function of temperature. So if we're at temperatures, at intermediate or high temperatures, we are BCC. Intermediate temperatures, we're in FCC. And actually, then we go back up to BCC. So this is going up in temperature, BCC, and then up to that. So if we go post plot, oh, it's not going to show plot. I'd have to reinitialize module. All right. It's step normal. So now it only calculates the equilibrium. So you can see at high temperatures, the free energy of the system is given by the liquid phase. Then here we go to BCC, we go to FCC, then we go back to BCC, we go down in temperature.
Can you scroll up real quick?
Sure.
Just so I can see those again. I missed that portion.
Yeah, so what we did is we did everything the same. We suspended our three phases here. First, I reinitiated the module way up here, right up here.
Yeah.
And then we changed the status. We suspended the three phases we don't care about. We set the axis variable. We compute equilibrium. And then this time when we stepped with options, I chose the default, which is normal. And so instead of calculating the free energy of each phase at each temperature step, it calculates the free energy, the equilibrium free energy at each phase, or at each temperature step. And so when we plot it, now it only plots the equilibrium free energy, or the free energy of the equilibrium phase as a function of temperature. Does that make sense?
Perfect. Yes. Yeah. I was missing the ST normal.
Okay. Okay. So as we were going through, there were some other things that people wanted to know. Was there anything somebody had said that they might want to look at using a unary system, or should I move on to a binary system?
Can we look at the G versus X curves if we change the stepping variable to the
G versus
Okay, that
X?
would be for a binary.
That's where I'm going next, Sabina.
Okay.
Yeah, so I wanted to start just by going on a unary system, because that's really the basic starting. I don't know how many people are going to be using that, but that's where I wanted to start. So something in the chat. Okay, Obed.
Yeah, that was me. Thank you very much.
Yep, the thing will be on phasetrans.utk.edu if you want to continue, because now we're going to get into a binary, and you can
Will
just
do.
skip the first hour and pick it up where you left off if you want. If you don't, I tend to talk a lot, so maybe you don't get much out of it.
I'll check it out. Thank you very much. Have a good one.
Very welcome. You too. Have a good weekend. Does everybody want to, that's still here, want to continue? We can go on to a binary system. Yes?
How do you clear your current plot? I just have a question.
How do you clear your current plot?
Yeah.
You can't clear your current plot unless you reinitiate the module. So this is the current plot that we have. If I go to post, I can open up a new plot, and if I plot again, it's going to plot the same thing. But if I go back, whoop, I didn't want to go back twice. And then I reinitiate the module and then go to post and try to plot it again. It gives me blank.
Okay.
And sometimes when you're plotting free energy functions, if you want to run a calculation and plot free energy at, when we do the binary, if you want to plot free energy at 1,000 degrees as a function of composition, you have to run that. Then you have to reinitiate the module and run it at your next temperature. Otherwise, it ends up plotting both.
Got it.
The free energy at your first temperature and the free energy at your second temperature, and it just keeps compiling on top of that. Now, why exactly it does that, I don't know.
Yeah, can you avoid that with like Python implementation?
Probably, yeah. I mean, if you use Python, I mean, you just call it once, and
and then dump the photo and then reset.
Yeah. I mean, and the thing I haven't showed yet is you can list the data. I should have did that. I'll list the data when I go to the binary system, but you can list the data and it will actually plot a list. And from Python, you'll probably just export that list of data and plot it in Python, right?
Okay, yeah.
Or, I mean, yeah, because that's one of the, beautiful things about being able to use Python is you can collect that data from ThermoCalc, pull it out, and then manipulate
Do whatever you want.
Do whatever you want with it. Okay, so let's go back to, let's go database. We're still in this one. Okay, so now I'm back in the database. So I want to start over. So I'm just going to reject the system. Hey, what's going on, Eric? Oh yeah, come on in. This is our normal group meeting. Yeah, if anybody wants to join us, we've got plenty of space in the executive conference room at Chime. We don't officially have it here, but if you're in the building or you come here and you want to join us in person, we're here most of the time. If somebody else is using the room, we'll have to do it all remotely. But anyway, okay, so I rejected the system. So now let's find some new elements. Let's do iron, chromium, and let's just do iron, chromium. What? Oh, no, not carb. So let's do iron and nickel. Reject. What's that? You'll have to reject elements Ni or chromium. Or you can just go reject system and start over. So we're not really concerned with all of these phases. So I listed the data base phases, and we're not really concerned with all these different ones with binary iron nickel. So one thing I can do, if I don't really care about a lot of these phases from the start, and I don't want to include them in my database retrieval, I can just select phases and list which phases. I can use the wildcard and it will actually reject all of them. And then I can restore phases and restore just the ones that I'm interested in. So let's try liquid, BCC, A2, FCC, A1. And so now when we go get, it will only retrieve that data and we don't have to deal with those other phases. when we go into polys. Now we'll go to P3. So as long as we're here, I'll show everybody how to calculate a binary phase diagram. So when we calculate a binary phase diagram, we need to do the same thing first as we did when we were doing the unary. We have to set our axes variables. So for a binary phase diagram, it's typically as a function of composition and temperature. So we'll set axis variable 1. Let's make it W for weight fraction nickel from 0 to 1.01. So when you're in poly and you want to do a calculation as a function of composition, you have two choices: either W parentheses of the element of choice, which is for weight fraction, or X, or mole fraction. When we go to plot it, you can plot it versus mole fraction, mole percent, weight percent, or lots of other things. The second axis, set axis variable 2t. My default is typically 500 to 2000, 10. If I'm doing a binary system, those are my default variables and step sizes. So we compute our equilibrium. Now we can list equilibrium to screen. And at 1177.75 Kelvin and a weight fraction of 0.1234 nickel, we have single phase FCC stable. So now when we want to actually calculate the phase diagram, instead of using that step, the step calculation is for a single axis variable. To do multiple axes, we do map. So we're going to map our equilibrium calculations out onto a grid. Map. And look at it go. Almost as impressive as using Maple to solve for equilibrium compositions. Did she tell you about that? She must have. Bush just spent the time to figure it out. Anyway, a further digression. Anyway, now that we've calculated it, we'll go to post. And again, the first time you go into post, it'll set automatic diagram axes. And if you look at it, it actually does a pretty good job. Sets mass fraction nickel, temperature in Kelvin, and bingo, bango, bongo. We've got. Oh, man. What did you get? You know what? That's okay. It's a difference in the database. You're using which version of ThermoCalc? 2019? 2019 or 2020? Okay, I'm using 2020.
But how do we get here? We're all using 2019, we get here for plot.
Well,
Where she does get that tail. She just doesn't hit the rest of it around.
that's wacky.
So, they must be not confused.
No, you're considering certain phases. What is that? DCA2? Okay, that shouldn't be it. That's weird. That's weird. Max, are you there? Did you try this?
Yep, it's exactly the same, but I accidentally zoomed in. How do I zoom out of the plot?
You have to go back and type plot again.
Man,
Is
Okay.
anybody else here following along, or is it just Max that's running it as he's following along? I don't care. I'm just wondering.
Okay, so I'm gonna give it to, oh, no, this is so much charging. Oh, that's
You should have set a new log file before you started this. Okay, so I don't really want to plot it as mass fraction. I'll say set diagram axis X for WP for weight percent. If you type in MP, that's mole percent. So we'll do the second diagram axis as weight percent. That's for what component? Nickel. Set diagram axis Y, TC. Let's plot it and see what it looks like. There we go. For those of you that don't know, set scaling status will let you change the range. Set scaling status, say for the X. Automatic scaling, no. Min value, 0. Let's try max value of 50 for 50 weight percent. Plot it again, and it does that. Okay, so that's, we did this in a little bit more detail last week, so I'm not going to spend more time on calculating a binary phase diagram. So let's just go back. I'm going to reinitiate the module, and we're going to do what we came here to do, which is plot the free energy functions as a function of composition. So we reinitiate the module. Let's set axis variable 1. We want to plot it as a function of composition. So I'll go W nickel 0.1. Let's look at our conditions. So now that I'm using an older version, it automatically sets P and N equal to 1. Who can tell me what degree of freedom I'm missing? Temperature. So let's set condition T equals, oh, what looks interesting? Say 600 degrees C, where we've got a couple of different things going through. So 600 is 873. If we list our conditions, we're at 0. That's good. That means we can do a calculation. Let's list our equilibrium. And at 600 degrees C and 0.1234 weight percent or weight fraction nickel, we have a two-phase mixture of 57.4% or mole percent FCC with a composition of 18.25 mass percent nickel, and the balance 42.6 mole percent, a mole fraction of 46.426 BCC phase with a composition of 4.3 weight percent. So now we've set one variable. So now we want to step separately to do each phase separately. It'll do, oh man, it's got a bunch of FCC phases. That's okay. They should all overlap on top of one another. Post, what? What's wrong, Melanie? What's wrong? We did binary phase diagram last week. It's something in ThermoCalc. So for those of you that are still here, ThermoCalc has a lot of quirks, which is one of the reasons I'm taking notes on things that go wonky, because we will continue to have quirks They are doing their best to have fewer quirks, but the way this code was written is it was code written on top of code, written on top of code. So you probably got 6 or 7 different programming languages written by 12 different coders over the course of the last, 35 years. And it's a mess.
It really shows too.
It does. And believe it or not, it is a lot better. The thermodynamic version of it is considerably better than DICTRA, than the diffusion module, because it's used more quirks have been found, they report them. But once you know what those quirks are, they're never complete failure quirks. They're not for the most part. I think I've found 1 or 2 things where the program just crashes. But for the most part, they're not, if we get this error, it's a complete failure. There are workarounds to it. You've just got, and that's part of playing with ThermoCalc, using it, getting to understand it, and trying to figure out how to get around it and do other things. And that's one of the things that Melanie and Serena are having one of the issues that they're having right now is they're not getting the same phase diagram because there's some quirk in it that they typed in the exact same thing and they got something different. Well, that's why. So, but there are things, usually if it's the same version, same database, same commands, you'll get the same thing. But if you change the version or you change the database, you might get something slightly different, but there are tricks that you learn to accommodate for that. I don't know if last week we had an issue where we didn't calculate a solidus or a liquidus curve, and we had to add an equilibrium. Did we add an equilibrium last week? Okay, well, we'll get to that when we get to multi-component phase diagrams, because when we do that, it does it all the time. Okay, so we calculated the free energy separately of all of the phases as a function of composition at 873. We went to post. Now let's set diagram axis X, weight percent nickel, set diagram axis Y, GM, star for wildcard, column number, star for everything. Let's plot it. Boom. Let's set labels F, plot it again. And so we have the black, which is liquid. We have the red, which is BCC, and we have the green, blue, light blue, and magenta all laid on top of each other that are all the FCC phase. Now you'll notice that we have FCC number 1, FCC number 2, FCC number 3, FCC number 4. These are what we call different composition sets. And they're used for ordering or miscibility gaps. Why there are 4 composition sets by default in this FE demo database, I don't know. But if you were looking at something like iron chrome, there's a miscibility gap in the BCC phase. So you would actually see BCC1 and BCC2, and your BCC curve would have a miscibility gap or a region of negative curvature in the free energy curve. What's that? Yes, 3, 4, 5, and 6 here are all the same curve in this case. If we had carbon in it, the MC carbide, so MC, right? Say niobium carbide. That carbide is modeled using the same FCC phase as FCC or L12. So there is a miscibility gap in the carbon content of your FCC phase description. So if you were to plot the free energy of the FCC phase as a function of carbon content, there would be one phase with a low carbon content, you know, very, very small, and there'd be one phase with a carbon content of roughly 50 atomic percent. And that is the MC phase. That is the MC carbide phase. And so one of these 4 FCC phases would actually be different because it will be plotting a different part of that curve. The same thing for an ordered phase. So if we were looking at nickel aluminum, and we can look at nickel aluminum, but I chose iron nickel right now, so we got to deal with it. If we were to look at iron nickel, one of those phases would be ordering. So we would have the pure FCC phase that would have one free energy curve. We would have the L12 phase that would be another curve, and over certain composition ranges, it might overlap because that may not be stable in that composition range. So actually what the ordered phase may look like is actually be a tail or an extension coming off of one of these. So maybe I can, no, I can't. But we'll do that some other time. So now we've got free energies as a function of composition. Kind of cool. Let's try something else. Let's go back to poly. I'm going to reinitiate the module just to start over. So one thing that we have not done yet is we can actually enter our own symbols and functions and tables and so forth. So what I want to do is, oh, we've got a comment, which is Sabina's helpful, make the mistake a step. Good. Good.
So what would happen if we step normally with this?
Why don't we do that? Let's do that instead of doing what I was going to do. So let's set axis variable 1 x, or we'll do w and I 0 to 1.01. Set axis variable 2 t. Wait, no, we're only doing 1, right? Sorry. We did this for a temperature of T equals 873. Let's list our conditions. 0 degrees of freedom. Compute the equilibrium. And now let's step normally. Now we can post. Set diagram axis X weight percent nickel. Set diagram axis Y GM star. There you go. So it plots only the free energy of the equilibrium phases. So over here at low nickel content where BCC is stable, it only calculates the free energy of BCC. Over here where FCC is stable at high nickel content, it only plots the free energy of the FCC phase. In here, where we have a 2-phase region, it plots the free energy of both. Why are those linear? It goes back to the free energy. The chemical potentials and the free energies of our phases in a 2-phase system, in a 2-phase region of a binary alloy, the chemical potentials are always the same. They're equal all the way across that. If the chemical potential of A and the chemical potential of B are equal, then the free energy of those phases are also equal all the way across that two-phase equilibrium. So they're constant. The only thing that's changing is the fraction of each phase, right? So that's why we get a constant free energy in that for BCC and FCC in this two-phase region. So if we were to plot our phase diagram again, I wish I would have saved it, and we would draw a line right at 600 degrees C or 873 K, we would see that up until, if you scroll your mouse over, it'll give you an estimate of where you're at. So up into about 4.5% nickel, BCC is stable. And then we go into a two-phase region of BCC plus FCC until we get to somewhere around 18% nickel, where we then go back into a single-phase region, this time of FCC. Oh, actually, if we want this data, we can go list data. And if we do it to a file, it will actually print out all of the data that it calculated. And if I were to, there's the data file. There's the data file. And why won't it let you save it? Did you type save to file? Okay, so yeah, so if you list this data to a file, you can actually save it. The other way you can grab that data is writing a Python script to say, bring that data to me. Unless you're like me and you're not smart enough to know Python, you could make an experimental data file, and that actually will make a plot of all of these curves and all of the axes, so that, you know, it'll actually make a data file to print this plot. And I'm not smart enough to know what that's called, but you can do it. I like lists because then I can pull it out and I can do whatever I want. So
Also, dump diagram just saves the plot, saves the image.
yes, dump. Well, if you're in dump, does save it as an image.
Thanks, Adina.
Or if you go over here and you right click, you can save as. You would. And so if you can save it as either a figure, or if you save it as an SVG, that's a scalable vector graphics, which means it's got all of the commands to print the file and not necessarily, it's not just an image. Yeah, I've never heard of it either until somebody taught me what it is. But it's basically something where smart people use it so that you don't have to save something as a picture with a certain resolution. If it's an SGV file, all the information on all the lines and data are in it, so that it will scale and have good resolution no matter where you have. So you can save it and you can blow it up to a bazillion and still have the same resolution, as it wouldn't look blurry like you save this.
There, some programs though really don't like using them. Like PowerPoint
Yes.
will slow right down if you try to
Yes.
use vector.
Yes, I have. I a lot of times will tend to save them as an SVG or maybe a PostScript, but if I import them to PowerPoint, I think by default my computer opens up an SGV file in Google Chrome or one of my internet browsers, and so I will open it up in Google Chrome. I will then copy that and paste that into my PDF, into my PowerPoint file. Why I do SVG, I think one day when one paper I was, somebody else was the lead author on, they wanted the graphics in an SVG file, and so I started doing it that way. If I'm just saving plots for, showing to a group or something like that, I'll probably just save it as a PNG or usually a PNG. If I'm saving it for a paper, I might do an SVG just to keep that resolution whatever I want until I get to the final product. I don't know if that makes any sense or not, but anyway.
Is there a way to use Python to programmatically enter in these codes?
Yeah. Yes. I'm actually
like if I want to make like a delta G curve for a bunch of different temperatures, right?
Yep.
It's kind of cumbersome to manually go through. So is that something you can
That
easily
is something
do?
you can do. That is not something I can teach you because I do not know Python. That is somebody that's sitting to my left could show you because he knows enough Python to be able to do that. Eric Heikkinen's over here, and I'm sure there are other people that know enough Python. There is what you call the TC Python interface for Python that you can just call everything. You write a Python script to call ThermoCalc, do a calculation, extract it. And what are you laughing at? Oh, me? Oh, okay. You can, but I don't know Python yet, which is a very frustrating thing. Yeah, it's a very sensitive topic because,
I'm sorry to bring it up.
Yeah, I know. I've been here at Tennessee for a year and a half now. I've had grad students for a year and a half now. Not all of my grad students have been here for a year and a half. But I've had grad students for a year and a half, and I've been telling my grad students to learn how to do Python because I want to do something very specific that somebody sitting to my left already knows how to do, but I can't do. And so it's very frustrating. So I've been trying to get my grad students to learn, and they haven't figured it out. And so I hired an undergrad to teach me how to do it. You did learn Python this week. Maybe I should have just hired Eric. What's that? Yeah, I mean, all I want is your code to plot dendrite tip temperature. That's all I want. And then be able to wrap something around it to be able to plot it at different temperature gradients and then be able to do that. But that's asking a lot. And so and the other thing I want to do is I want to do something with Serena to be able to look at chemical short range ordering and HEAs, which we need to be able to just extract the data from ThermoCalc to do. TC Python is perfect to do that, but I don't know how to use Python. But anyway, long story short, I digress, Max. Yes, you can. And under the ThermoCalc help, you can go to the manuals folder. And I believe that the ThermoCalc documentation set here actually has the instructions for installing TC Python. If you have not already done so, do that.
Perfect.
And if you already know Python, you are golden. And now that you're learning ThermoCalc, I may have you have someone like Melanie and or Serena look over your shoulder while you're writing that code.
Yeah, if I do anything, it'll be for precipitate phase formation in
Yep.
Aluminum alloys. So if I can run through, so that's probably what I'll try to approach.
Yeah, you're looking at the aluminum cerium alloys, right?
Yeah.
Yeah.
Adding copper and then different grain refiners.
Yep. Gotcha. Okay. It is 10 after 4. Oh yeah, let me do one more thing. You can leave. Okay. I want to do one more thing, and that will complete plotting free energy functions. And it will also give you guys one more thing that you can do. I was talking about symbols. So let's go back to Poly. I'm going to reinitiate module. I was talking about symbols, and I want to enter a symbol. And it will say, do you want to enter a constant, a variable, a function, or a table? And you can do any of them. You can enter a function, which could be a function of the different properties. So if you want to plot, if you want to enter a function that is a, can we plot the difference? Yeah, that's exactly what I was going to do, Sabina. I think.
Got it. Okay.
I think. So what I'm going to do is I'm going to set up a table. I'm going to name it DG. And actually, shoot, I think I need to see GM liquid. Let me see if I get this right. Minus GM BCC. So I think that works. So I can enter. All right, let me enter a function. Enter a symbol, a function. We'll call it DGB. And that function I'm going to define as the difference between the molar Gibbs free energy to the liquid and the molar free energy of the BCC phase. Which one? You could have. Did you get the error under table when you were doing table? Well, yeah. So do this, Melanie. Do these things right here. Enter symbol, function, give your function a name, and then GM liquid minus GM BCCA2. I'm going to enter a second symbol, another function. I'm going to name it DGF. I'm going to make that the difference between the free energy of the liquid phase and the free energy of the FCC A1 phase. And now I'm going to enter a symbol, a table. I'm going to name that table DGM. It's going to ask for variables, and I think if I did this right, I can make it DGB and DGF. So now I have a table of those two values. So now if I go back and I plot the free energies of these phases as a function of composition separately, can compute the equilibrium, we can step it. Oh, dang it. Dang it.
But so at this stage, you're resetting the module because you went and stepped it normally?
Because I stepped it normally.
But what if we just went back, I mean, just stepped it with separate phases again? Wouldn't it do the same calculation?
It adds on.
Okay.
It adds on, so it would have done the calculation, but I believe that if we plotted it, it would plot this plus the other thing.
Plus
And
the
it
other
would
one,
be
okay.
all, and I don't know why it does that. Yeah, you're right. Separately, good. Post. Now set diagram axis X weight percent nickel. Oh shoot, I didn't make the table. So there you go. So now what we've done is we've plotted the free energy differences, the difference in free energy of the liquid phase and solid phase. So this is all relative to the liquid phase. So if we were to plot this up where the liquid was stable at something, we would actually see those numbers become positive. Is that what you wanted to see, Sabina?
Yes, I just wanted, yeah,
Yeah.
I want to see.
Yeah.
the
So I didn't choose the best either reference state or the best temperature to do it, but yeah. So these are now the difference in free energy. So really, these would be the driving forces for solidification of BCC and FCC at 873.
600.
Yeah, or 673. Sorry, 400. Okay, so that's where we're going to have to stop today. Excellent. I was a little surprised that it goes wonky like that, but that's the FCC. Yeah. Before we go, are there any questions? I see somebody left, whoever that was. Any questions from anybody still here?
How do you save? Like, do you save?
Save what? Oh, that's a good thing. Well, the set log saves all of your commands. So now if I were to go back and I were to open macro at the system, it would do all of the commands that I've done. You would have everything from, yeah, it will have everything. Unless you type exit. Once you type exit, that basically resets Thermo-Calc. And so then your log, so then you have to restart your log. But you can also save your calculation environment if you go under save workspaces. So you can save your workspace and it will save basically what the calculations that you've performed right here. So if you just wanted to have access to this and manipulate this, the data from this calculation, you could save this workspace. So then you would open, next time you wanted it, you would open up ThermoCalc, you would go to the poly module, and you would open, is that, where's open? It's open here? Oh, read. You would read workspaces, and it would bring you right back to this point. It wouldn't plot it for you, but it would have all of the data that all you'd have to do is go to post, set your diagram axes, and plot it. Okay. So I have a meeting at 4:30. I want to take a quick break before, and so I will pick this up again next week. Thank you all for joining. I hope you got something out of it. If you have any questions, you can always shoot me an email, and I can help. Otherwise, feel free to come back next week. Feel free to, I will put this recording up on the webpage so you can go back and watch it. If you don't want to come to the meeting, but you want to watch them, you can watch them at your leisure. I'll continue to post them. And yeah, hopefully you guys will get something out of it. And once we get comfortable using ThermoCalc, we can move forward and actually apply it to your research. So thanks, everybody. Have a great weekend. I will hopefully see or talk to you virtually next week.
Thank you.
You're very welcome.
Thank you.
Thank you.
Thank you. Have a good weekend.
Bye, everybody. Have a great weekend.
I like this.